Okay, cool. So before we get started, I think I'm supposed to tell you that you should not bring drinks or food in here. So if you have a drink, there's a spot outside, I'm looking at you, where you can put them. Here you go. Yeah, cool. Okay, great. Other than that, I think we're running a couple minutes behind, so I'll be quick. The next speaker is Alex Warstadt from UCSD Linguistics.
Okay, great. The mic is on. So yeah, the title of my talk today is Why It Matters That Babies and Language Models Are the Only Known Language Learners. So I'll be talking about a bunch of work that I've been doing recently. Some of it actually hasn't officially been published yet, but everything should be available on my website in case you're interested in finding the manuscripts. Okay. So the premise of the talk, for most of human history, or most of history, I guess human history, humans were the only thing in the universe that could learn language. Okay, so here's a little timeline of human history. You can see things that learn language. Humans are the only thing up until very recently. Okay, so maybe whether or not language models are actually learning language might be a matter of debate or a matter of semantics, but I think it's clear that they're doing something like learning language pretty well. Whether or not it's complete, the process, it's certainly an ongoing process. And they're certainly doing something interesting. So in the last few years, language models have made humans seem a little bit less unique in our place in the universe. Okay, so on the one hand, we have transformers, language models. On the other hand, we have babies. And I'm interested in how can we use one of these things to learn about the other. A lot of what I'm going to be talking about is how we can use language models to learn about babies, but I'm going to start actually with a little bit of the reverse. So just to give a little teaser, this is a comparison of the amount of data that's been input to different language models compared to humans. And as you can see, today's modern large language models have close to 15 trillion tokens or more than that of input, whereas an adolescent human might have been exposed to about 100 million words. So this is a difference of 5 orders of magnitude. So humans are, language models are very impressive, but from this data efficiency perspective, humans are actually, I think, extremely impressive when we consider how much input it takes to train an effective language model. Next, one of the ways that I think is really exciting to use language models to study humans is controlled experiments. So these are pictures of people who allegedly conducted controlled experiments on children acquiring language. They deprived children of language in various situations, and they had some kind of strange questions that they were trying to answer, like what was the original human language or something. I think the exact motivations of these people, the specific motivations of these people is not important, but the general idea that if you want to answer some kind of causal question about the impact of the environment on language development, the best way to do that from a purely scientific perspective is a controlled experiment, right? That's the gold standard of evidence for making causal inferences. Obviously, for ethical reasons, this is impossible in the modern day. And it was also kind of impossible in those days, right? We don't have the ability to control the full environment, the full input to a child as much as we would like to answer the kinds of questions that linguists and cognitive scientists are generally interested in. Okay. So another case for using language models in linguistics and cognitive science is that they can help us answer what do language learners look like in general. So I think for the entire history of linguistics, we've operated in sort of a heliocentric system, so to speak, where humans are sort of the center of the universe. Humans are the only thing that can learn language. We're special. This is our assumption. Now, maybe we can start to have a little bit of a Copernican shift and ask, well, what does a general language learner look like? And we can start to think, okay, maybe humans are just one representative of this concept of a general language learner. And under that this new concept that we can start to think about, maybe humans are not actually particularly unique, or we want to think about what does it mean for, how can we conceptualize a general language learner, a set of language learners under which humans would just be kind of a typical sample from that set. Of course, there is something special about the Earth from certain perspectives. It might not be the center of the universe, but there's the anthropic principle, right? If you're interested in questions like what are the conditions for life? Well, it's not random to study the Earth. The Earth is not typical compared to all other planets. So you can say there's a similar analogy for humans, right? Humans are not just a random language learner. Natural language is something that evolved for human use and with human language learners. So there is maybe something special. And so we can try to tease apart by looking at other language learners, just like we can look at other solar systems. What are the properties of humans that are unique among language learners versus properties that maybe are shared across a bunch of language learners? And a bunch of language learners might be something that we have in the future. Right now, we have these transformer language models, but 2 samples is a lot better than 1. And then the final, I think, real big benefit of language models for linguistics and developmental science is what can you learn with domain general biases? So arguably, models like the transformer have domain general biases, right? They have been successfully adapted to modeling vision, things like protein folding. These are domains that have nothing to do with language processing. And these models are extremely successful in these domains. These are not obscure works. These are works with tens of thousands of citations that have been extremely successful. So I think it's fair to say that whatever inductive bias it is that allows transformers to be so successful at language learning, it's probably not something that's super specific to language, because it's also equally what seems to be well suited to a bunch of other domains. So this is really important because we can start to study what are the kinds of properties of language that can be learned by a learner that doesn't have language-specific biases. And maybe this can give us some evidence about whether language-specific biases are necessary for particular aspects of human language learning. Okay, so a roadmap for the talk. I'm going to go in 3 parts. First, I'll talk about the modeling side of things. So this is the more engineering-focused portion, where I talk about how we can use insights about human language learning to maybe improve NLP applications. And second, I'm going to talk about comparing, so looking at different properties of the learning trajectories of language models and comparing those trajectories to those of humans. And then finally, controlling, so doing these kinds of controlled experiments where we manipulate some aspect of the input to language models and try to make some causal inferences. Okay, so let's get started with modeling. So first, I'm going to start by talking about the BabyLM challenge. So this is a shared task that's been running for the last 2 years that I'm an organizer of. The last 2 years, it was at Connell, and this year it's going to be a workshop at EMNLP. Okay, so the starting motivation for BabyLM is that humans are much better language learners than LMs in terms of data efficiency. So I already showed this figure, the comparison between the input to language models and humans. You might also ask, okay, well, there are small language models available. How do they perform on language? And here, I'm comparing the grammatical performance of small language models trained on 100 million words to humans on acceptability judgments. And you can see there's a pretty consistent gap between the small language models and the humans. So there is actually a data efficiency gap. Okay, so that's part of the motivation behind BabyLM, but actually we have these 3 things that are motivating the competition and workshop. So first, data efficient pre-training. I already talked about this a bunch. The second is building plausible cognitive models. So this is an open call to the community to develop techniques that will result in more developmentally plausible and cognitively plausible language models. And these types of models will be really useful for the kinds of experiments that I'm going to talk about later. And then finally, we're interested in democratizing pre-training research. So I think pre-training language models, training language models from scratch, this is something that's become increasingly concentrated in a small number of really well-funded industry labs because it's so expensive. And I think because in academia, we might think it takes so much money to pre-train these models, I don't stand a chance of training a model that's going to compete with a GPT or a DeepSeek, so I'm not even going to bother. But what we're trying to suggest is that actually there are a bunch of interesting research questions that can be addressed by training small language models at the kind of scale of human language acquisition and the kind of scale that is very easy to do on an academic budget. Okay, so BabyLM, a big portion of it is that it's a shared task. So the parameters of the shared task are actually split into 3 separate tracks. We have a strict track where you're given up to 100 million words and a shared evaluation. A strict small track where you get just 10 million words. So that's maybe the amount of input to a 1 or 2-year-old infant. And then we also have a multimodal track, which allows participants to use unlimited visual data. And we have a released vision and language data set, but participants can also bring their own data. And we also have an additional vision and language evaluation. And then we also welcome submissions that are not tied to one of these competitions, but just original research related to data efficiency or cognitive plausibility. Okay, so what does this training data set that we've released look like? You've heard about it a little bit from Kyle already, who used it in some of his experiments. So there's no fully developmentally plausible source of input for training language models. There are some really nice collections of input to children, but they're not at the scale that's necessary for training models that have the amount of input as an adolescent. So we're trying to sort of balance scale and plausibility here. So the first thing that we do is we try to source a lot of data from transcribed speech. So more than half the data is transcribed speech, which much more closely resembles the input to children than, say, like edited Wikipedia articles or something. We're also trying to get a large portion of child-level data, so simple domains with simple sentence structures, smaller vocabularies. And then at the intersection of these two, the single largest data source is Childus. This is this great corpus of child-directed speech or interactions between caregivers and children. What do the evaluations look like? Well, there's BLIMP, which is a test of acceptability judgments. We have GLUE and SuperGLUE. These are tasks that you fine-tune on that are testing for things like language understanding, things like question answering. And then we also had some hidden tasks in both years that the competition ran. So we had an additional supplement to BLIMP, including some sort of discourse level phenomena, some generalization tests, and then some tests of world knowledge. I'll just give a little bit of an overview of what BLIMP looks like. So linguists really love to give examples of grammatical and ungrammatical sentences in their work. Kyle has already talked a little bit about acceptability. One way that these examples are often presented is as minimal pairs. So these are two sentences that differ in acceptability, but also are very similar to each other. And these are really great because they zoom in on this decision boundary between acceptable and unacceptable. And that decision boundary is not simple. This is a really complex decision boundary. So it's very important to get really zoomed in close to that boundary. Second is they're reproducible. So these judgments are gradient. And if you ask humans to give gradient judgments, you make a forced choice. Which sentence do they prefer? That method of getting acceptability judgments is a lot more reproducible, and there's much higher agreement than if you just give people one sentence at a time. And then the biggest advantage for using language models is that we can test language models in an unsupervised way. Right? So language models are already trained to give us probabilities for strings, so we can just ask, do they assign higher probability to a grammatical sentence than an ungrammatical one? Okay, So this is what BLIMP looks like. It has these 12 different categories covering a bunch of areas of syntax and morphology and semantics. This is a data set that I worked on during my PhD. So what do we find for the first couple of BabyLM challenges? Well, in year 1 and year 2, we both got exactly 31 submissions. And this is the results. This is the breakdown for year 1. But both years, we found that the strict small track was really popular. So people really like training language models on 10 million words because it's cheap, it's fast, you can train a bunch of models. We also broke down submissions by the techniques that people used. So you can see that the most popular technique that in submissions was curriculum learning, right? So this is a method where you try to design the order of the inputs, maybe to start from simpler, shorter sentences or simpler vocabulary and expand over the course of training. But there's many different ways to design a curriculum. Okay, so this is all of the submissions to the BabyLM challenge. You can see that the largest gains that we saw were from architectural modifications. This is just one submission. It happened to win the challenge in the first year, and I'll describe what it is that they did later on. This curriculum learning approach that was super popular is kind of in the middle of the track. It doesn't really lead to any notable improvements. And then multimodal, we got a very small number of submissions, and they were very inconsistent, but generally not particularly helpful. So this is still an ongoing challenge. Okay, so this winning submission, what did they do? Well, they designed this new model architecture, which they call LTG-BERT. And what's special about this architecture? Well, kind of a lot of things and not so many things at once. So they modify sort of the typical BERT masked language model architecture in maybe 4 or 5 different ways. What those ways are sort of things that were taken from developments in the machine learning literature over the last few years, like putting layer norms in different places, having disentangled attention, having a different random initialization, and just kind of combining them into one model. So this model is unique in that it's different from typical masked language models like BERT, but maybe it's not so interesting in the sense that they didn't really do anything cognitively plausible. They just sort of threw a bag of tricks into one architecture. Okay, but what did the results look like? Well, here I'm showing results from the Llama 2 Skyline. So this is a model that was trained on trillions of tokens of input. And you can see the performance on all of our evaluations. And then this LTG-BERT model, by comparison, is actually outperforming Llama on a lot of evaluations and is close to Llama performance on some other ones. So this is a model that was trained on maybe 4 orders of magnitude less data, but it's actually comparable performance or even better performance than a really large model. So say what you will about how interesting these architectural innovations are, but the results I think are quite striking. Now, one thing I will say is that this approach hasn't been scaled up to the kind of training data scale for a model like Llama. So it's not clear if these gains will continue to scale to larger training sets. So that's something that is yet to be done. Okay. An open challenge that I mentioned is multimodality. So these are the submissions from the last year's multimodal track, and you can see they're all really close to our baselines. That's this dashed line that we released, and really, really far from human performance. I tried to throw my hat into the ring. We were asking whether increasing the amount of vision data for a fixed quantity of text data could improve performance. So you can see here, this is for like 10 million words and different amounts of image data. You don't really get any gains. And for 100 million words, it's kind of the same. So adding vision data in the setting that we were looking at doesn't actually seem to help with language learning, even though I think intuitively, it's kind of obvious that children are benefiting from having some kind of sensory input. So this is, I think, a modeling problem, not a conceptual problem that needs to be solved. Okay, so what's new for BabyLM? Well, one thing that one of the submissions from a previous year found is that cognitive plausibility of models, as measured by how well you can predict reading times, is negatively correlated with performance on the evaluations that we included in the shared task. So this is clearly counter to one of the stated goals of BabyLM, and so this year we're working on a cognitive plausibility benchmark that will hope to sort of balance these two goals a little bit better. And then second, we've added an interaction track. So we're encouraging participants to include some kind of interactive training objective in the pipeline, where you have interaction between two agents, maybe a learner model and a pre-trained large language model or something. As I said before, we have a workshop at EMNLP in Suzhou, China. So that's the modeling portion. Now I want to get into the more cognitively oriented stuff, using language models to actually comparing them to human language acquisition. So that's part 2. Okay, so why compare learning trajectories in humans and language models? I think there's a bunch of reasons. One, of course, is just a sort of evaluation. So we really need to establish the plausibility of model learners. And if we find that they're falling short, then we want to use these evaluations to improve their cognitive plausibility. And having similar learning trajectories, this is one dimension of being a plausible model learner. And this is important because as the developmental plausibility of your model learner increases, the generalizability of results from experiments on those models to humans increases. So maybe this isn't a line, maybe it's actually something more like this. But there's clearly some positive relationship between these two things. Also, looking at the trajectories gives us sort of a metric for allowing us to reverse engineer the sufficient components of human language learning. And this is something that Emmanuel talked about in his talk yesterday. And then third is we can help to determine what's idiosyncratic about humans. That is, what's likely to be innate. So this relates back to what I was saying about the sort of Copernican principle for language learners. We can try to sort of map out the space of conceptual language learners by looking at just not one sample from this set, but a couple of samples, and see is it sort of the null hypothesis that humans are typical true, and where is that hypothesis false? Okay. So first, I'll talk about some work that I've been doing on word learning. Okay, so as I said before, comparing learning trajectories in language models and humans is important for developing plausible model learners. But how do we actually compare trajectories between humans and BabyLMs? One thing you might want to try is to compare acceptability judgment trajectories. Right, so there's this nice paper from a couple of years ago that tries to do this. They get all of this great data for sort of the order of acquisition for all of the different phenomena that are included in the BLIMP benchmark for acceptability judgments. And then they compare this to some human data. Okay, so what does that human data look like? Well, it's this conclusion from this recent study that found, well, first children seem to learn simple sentences, then they learn WH questions, then they learn relative clauses. So I'm not trying to bash this work or this paper. The point that I'm trying to make here is the amount of data that we have about the acquisition of acceptability judgments is really, really impoverished compared to the amount of data that we can measure from language models. And the alignment between these two things is really poor. So it's very difficult to get acceptability judgments from children. They don't, 4-year-olds, 3-year-olds don't like to answer that type of question, which is why this data has been fairly limited. So a better alternative maybe is word learning. So we have all of this great data on word learning, which a lot of it is due to Mike Frank's work. I think we're going to hear from him later on in the week. All right, so you have parents report on children's lexical knowledge, whether they're producing a word, whether they understand a word at different ages. And then you can draw sort of this curve for at which age do children acquire particular words. And you can do a similar or you can do something, maybe not a similar methodology, but you can also draw a learning curve for particular words for language models. So in this curve, we're plotting the surprisal of a model's surprisal for a particular word across different training steps. And you can see these curves look kind of similar, although BERT is on a log scale and children are not. Okay, so now the obvious question, are language model learning trajectories human-like? Well, the answer is a resounding no. So this earlier work by Chang and Bergen found that frequency, the frequency of a word in the training corpus is highly predictive of the order of acquisition. Whereas in children, this relationship is a lot weaker. Things like concreteness of the word are actually much more important for predicting the order of acquisition. Okay, but you might ask, well, what does it mean to learn a word? How do we measure word learning in language models? One of the obvious things to reach for is the distributional hypothesis, right? So this has sort of been the driver of a lot of the developments in natural language processing around word embeddings, which have later led to contextual word embeddings, which are used in transformer models. So how do we define a distributional notion of word knowledge? Well, this earlier paper that I talked about by Chang and Bergen, they do have some kind of distributional notion. What they're doing is they're measuring the surprisal of the word in context. What we do in this paper is we formalize this a little bit and say, okay, you can define a distributional signature. This is how, some measure of how well a model is capturing the distribution of a word at a particular point in time. And this is, in this case, you measure the surprisal in various contexts, weighted by the context probability. And this, you can do a Monte Carlo estimate, which is basically just sample all the contexts where the words occur, measure the surprisal, and average them together. Okay, but what about knowing where a word doesn't occur? This seems to be an important aspect of distributional information as well, which was left out in this earlier work. So we can very easily just design in a sort of analogous distributional signature, where instead of sampling all the positive contexts, we're sampling negative contexts where the word doesn't occur, and then averaging these surprisals together. And we kind of went crazy and developed a whole typology of distributional signatures. These are the ones that I introduced before. You can also look at all of the contexts together. What I think is also interesting is instead of just saying, well, either the word occurred or it didn't, you can say, I want to compare to the actual underlying distribution, how likely is the word in various contexts. We don't have access to that distribution, but we can use a large language model as a reference model, as an approximation for that distribution, and say how similar is our learner model's probability to this reference distribution's probability in a bunch of different contexts. Okay, so what do our experiments look like? Well, we trained a bunch of BabyLMs on different data sets. So we started with a childless data set. This is about 29 million words, the full BabyLM corpus, and then a larger data set with Wikipedia and some subtitle data. And then we trained 3 copies of GPT-2 on each of these corpora and got a bunch of word learning trajectories. So this is, each of these plots is showing one of our signatures that we had defined, and then for a sample of words that we picked out. And then also you can compare to children. And this is kind of too much information to walk through, but I'll just point out a few obvious things. So this is the signature that was used in that previous work by Chang and Bergen. You can see surprisal goes down as learning goes on, so that's not too surprising. This is this negative context signature. You can see surprisal tends to go up as learning goes on. So models are learning to be more surprised by the occurrence of a word in implausible contexts. And then these are these signatures that compare to a reference distribution, and they pretty uniformly are decreasing throughout training. So the model is getting more similar to this approximation of the ground truth. And then we want to define some particular metric from all of these learning curves, right? This trajectory is kind of too much information to maybe make interesting conclusions from. So we can summarize it by extracting a single age of acquisition. That is a point on this curve where we say the model has learned the word. And the way that we define that is by convergence, right? So when this curve stops changing by within some epsilon. Yeah, question.
A quick question about the plots. In a couple of these plots, there seems to be a bit of a like a U shape close to the start.
Yeah.
Do you know what's going on with that? Or?
Yeah, so I think early on, the model distributions look very uniform, right? They're assigning relatively uniform surprisal to every word. Early on in training, they sort of learn the unigram distribution, so just the frequency of that model. And so if that unigram frequency is higher than average, then the surprisal is going to dip early on because it just is guessing that word more than it would if it was uniformly guessing across words. Okay, so now the real question, do any of these signatures have trajectories that look human-like? So we went through this trouble of defining all of these different distributional signatures, maybe in the hope that one of these is actually sort of capturing the true distributional knowledge of language models better than this previous work. Well, the answer is actually a resounding no. So none of the distributional signatures that we defined across any of the training data sets led to any kind of strong positive correlation. In fact, most of these correlations with child age of acquisitions are negative. So language models seem really to not be, at least based on this distributional approach, seem really not to be learning words in the same order as children. I'll skip this for time. Okay, so is this surprising? Is this expected? Why don't language models have human-like trajectories? I think there's a kind of some obvious ways in which maybe this is expected. I mean, one thing that you might ask is maybe just the training distributions are so different. I think this might not be a super convincing position because we did train language models on Childis, right, which is a corpus of transcribed conversations between children and adults. This looks a lot like the distribution that child learners have, yet we really don't find any effect of having a more plausible distribution leading to more plausible learning trajectories. And there's, you might say, grounding. So clearly, having some kind of sensory experience of the world ought to affect which words are salient for children to learn. And I think intuitively this is a really nice explanation for why concrete nouns tend to be the words that children learn earliest. And actually there's some nice work using visually grounded models and increasing the amount of grounded input, so similar to what I tried to do in my previous work, but they actually found that as you increase the amount of grounded input to the models, the similarity to humans on some judgments is increasing. So this seems like it might be correct. Then there's interaction, right? So children are interacting with caregivers, with adults, and they're producing utterances that are useful in those interactions. And the sets of words that might be useful for interacting might not be the same set of words that are useful for predicting a corpus. Related to this are production constraints. So children don't come out spewing long strings of text like a language model might do at the beginning of its training. Children are highly limited in their production. They go through stages where they can only produce one-word or two-word utterances. And so the words that they might choose to produce, given this production constraint, might be very different from the words that a language model might output without any constraints. Another thing is cross-entropy loss. So I think Surya talked about this yesterday. Cross-entropy loss is, this is the objective that we're trying to minimize, and it's incentivizing a certain kind of distributional learning, which again is not really the objective that children are optimizing. Okay, and there's probably many other things. Okay, so that sort of wraps up word learning, but there's another kind of learning trajectory comparison that I think is interesting to do. And in particular, I want to give an example of how comparing learning trajectories can tell us something about the idiosyncrasies of humans. That is, which aspects of the human learning trajectory are likely to be innate to humans. And again, reverse engineering is something that will come up in this next section. So in this section, I'm going to talk about the critical period for language acquisition in humans and language models. Okay, first things first, what is the critical period for language acquisition? There's kind of a bunch of things that fall under this heading, this name of critical period. The first thing that usually comes to mind is the critical period for second language acquisition. Right, so as the age of exposure to your second language increases, your proficiency in learning in that second language decreases. Right? Late L2 learners tend to be worse than early L2 learners. And there's a lot of experimental evidence showing this, as well as just the intuitive fact that this is true. There's also a critical period for L1 attrition. Right? So attrition, this is loss of proficiency in a language. In particular, as the age where if you happen to stop having exposure to your first language, if that happens earlier on in life, then attrition of your first language can be more profound. So this was shown famously in a case of Korean adoptees in France, that young children who were adopted and lost exposure to Korean had more profound loss of Korean proficiency than older children. So both of these are things where are effects that are correlated with the degree of development. Okay, but the question that is in the background or in the foreground of a lot of research on the critical period is why? What causes the critical period? And we can put up this very simplified summary of the two main camps. Right? You could say we could have a nature account or a nurture account of the critical period. There's a bunch of things a bunch of mechanisms that might be used to give a nature account. You might say have a universal grammar, like a Chomsky-style universal grammar, or you might have a more like biological or neurological explanation for critical period effects, like synaptic pruning in adolescence might lead to a decrease in neural plasticity or something. What does the nurture account look like? Well, this was an idea that was popular among the connectionists in like the 80s, 90s, 2000s. They had this idea of entrenchment, where they argued that for any statistical learner, when you first start out learning, you're sort of at the top of this loss landscape, and you can sort of get anywhere in this landscape, anywhere in the hypothesis space relatively easily, given sufficient data. But as learning goes on, you sort of get stuck in some local minimum in this landscape, and it might be difficult to access other parts of the loss landscape. So this might explain why there's a loss in plasticity in humans as we acquire a first language. At the beginning of learning, we can sort of learn any language that we like, but as we go on, as we develop and learn our first language, we get entrenched in the properties of that first language. How can BabyLMs tell us something, inform this debate about the critical period? Well, you could try formulating two hypotheses about the critical period. I'm calling them the strong innate and the strong experiential hypothesis. So this one, these are both hypotheses that maybe are a little bit too strong for anyone to advocate for, but they're useful for this thought exercise. Right, so one camp might say innate learning constraints are necessary to explain critical period effects. The other camp might say that critical period effects are a necessary consequence of statistical learning. And it's quite clear that if language models do show critical period effects, given that they don't have innate learning constraints driving them to have a loss in plasticity, then this would rule out this hypothesis. And if they don't show critical period effects, it would rule out this hypothesis. What about a slightly more nuanced view? So the weak innate hypothesis, innate learning constraints are the main driver of critical period effects in an arbitrary learner, or the weak experiential hypothesis, statistical learning is the driver of critical period effects. So here I'm making reference to this idea of an arbitrary learner. Right? This is relating again to this idea that of the space of possible language learners, and considering maybe there's this conceptual space of what effective language learners look like. Language models and humans are maybe just two samples from that space, and whatever is true of one of these learners based on a sort of Copernican principle for language learning. The null hypothesis is that most of the things in this space look kind of similar, have a lot of shared properties. So if we do find that language models show critical period effects without some innate bias, maybe we can conclude that that's kind of a general property of a lot of the elements of this set of language learners. And most likely humans would share that property as well, assuming we don't have some additional evidence to convince us otherwise. Okay, so we simulated a bunch of different training conditions, or we had a bunch of different training conditions that simulate like different learning trajectories or learning patterns in children. So we simulated a monolingual learner. This is a model that's just exposed to English. A simultaneous bilingual. This is a model that gets exposure to English and a second language throughout training. A late L2 learner. This model is exposed first to a non-English language and then second to English. And then we also have this fourth setting where we try to sort of reverse engineer critical period effects by reducing the plasticity of the model partway during training. We trained models on a bunch of different languages. I won't spend too much time on the details. We trained 2 different architectures. Some more training details. Tokenization and training schedule, these things are kind of important, but I'll skip over them for the sake of time. And then we evaluate on a bunch of different things, but I'll focus on BLIMP and perplexity. Okay, so what do the results look like? The main question, do language models show human-like L2 critical period effects, right? So as the age of exposure to L2 increases, does proficiency go down? So we have these plots where we have the number of epochs, the number of training epochs on the x-axis, and then the BLIMP accuracy on the y-axis for our 2 models. This is what monolingual models look like. You can see the accuracy goes up over time. We don't show what they look like randomly initialized, but random accuracy would be 0.5. So there's you should imagine a big increase from epoch 0 to epoch 1. And this is what a late L2 learner looks like, right? So this is simulating someone who learns a second language late in life. You can see it looks pretty similar, but maybe there's a little bit of a delay in learning. Big question, what does the simultaneous, the early L1, or early L2 learner look like? Well, they actually look a lot worse than the late L2 learner. They have a much more delayed learning trajectory, right? And this is the opposite of what we would expect from humans, right? In humans, learning a second language earlier or simultaneous with your first language leads to high proficiency, whereas in language models, it seems to be harming the proficiency and the speed of learning. LLMs are the opposite of humans. Okay, what about the L1 critical period effect? Do we get language attrition happening? Well, in monolingual models, obviously there's no attrition. We changed the training corpus halfway through just to sort of match what was happening in the late L2 learner condition, but there's obviously no attrition happening. The simultaneous models, also obviously there's no attrition because they have continued exposure to both L1 and L2. But then the late L2 learner, where we stop exposure to L1, has profound attrition of the first language. Right. So, and this is after training for 6 epochs on L1. So humans don't get 6 epochs of exposure to their first language, right? So, and even so, after just one epoch essentially of training, humans don't have language attrition, but language models seem to do so. So, again, language models are not showing a human-like critical period effect here. And then finally, can we reverse engineer critical period effects? So these are, just as a reminder, this is what these previous curves look like. For this setting, we applied this regularizer called elastic weight consolidation. This is a regularizer that basically you sort of save a copy of the model after training on L1. And then as you train on L2, you apply a penalty to the loss when the model deviates from what that copy of the model looked like after L1 training. So you're sort of incentivizing the model to remain close in the parameter space to where it was after learning L1. This is, I think, intuitively a way to sort of reduce the plasticity of the model halfway through training. So we're not reducing plasticity smoothly. We're just saying halfway through training, let's tank the plasticity. And this has exactly the effect that we want, right? It harms L2 learning quite a bit in the late L2 condition. And then how about for L1 attrition? It also prevents a lot of L1 attrition. You still see a little bit of a increase in perplexity that is worse performance, but the difference is much smaller. Okay, so that was part 2. In the time that I have left, I'm going to give, I think, part of. Oh yeah, question. Yeah, so we're just measuring the perplexity on the first language. So perplexity is this generalized measure of how well the model basically can predict the training corpus. And so we see as perplexity increases, it means the model is doing a bad job of predicting the training corpus. We also have plots in the paper for BLIMP. We only have BLIMP for English, so we have to sort of swap our experiments and train on English first, and then a non-English language second, which is the opposite of what we usually do. Okay. So part 3, controlled experiments on language models. Okay, so controlled experiments, I think, are really important and exciting because they can allow us to make causal inferences, right, about the impact of the environment on learning. And they can also help us to determine whether learning biases are domain general or language specific in humans. So I'll talk about one recent paper that that is under review right now, looking at typology, typological correlations in human language. So a question that is of interest to the whole enterprise of generative linguistics is, why are some types of grammars common across the world's languages while others are not? Right, so early on in the history of generative linguistics, Greenberg identified this set of universals that these are grammatical properties that tend to occur sort of in pairs across the world's languages. This was refined, has been refined over in a bunch of ways, but a really important update was by Dreyer in 1993. The way that he formulated it is you have a bunch of elements, things like verbs, adpositions on the one hand, and then things like objects, noun phrases on the other hand, and the relative ordering of this set with respect to this set tends to be the same across for a given language. So if you have a language where the verb precedes the object, then most likely the adposition will precede the noun, and vice versa. So another way to think of this is that this is often summarized as head initial versus head final languages. Right? There's languages where these head type expressions tend to come first, and then there's languages where these things tend to come final. Okay, so basically, from the beginning of the identification of these typological correlations, learnability has been one of the favorite explanations. Right? The first version of this universal grammar basically says there are some innate learning constraints that humans are born with, And these restrict the kinds of languages that we're able to learn to exactly those languages that are typologically plausible. And this was sort of refined into a theory of principles and parameters. Maybe there are some parameters, some limited set of parameters that can get set during development, but those which parameters are available limit the space of possible human languages. Okay. And then there's also some experimental evidence for learnability, for typologically implausible languages being less learnable than plausible languages. This is work by Jenny Culbertson. She's done a bunch of work in this area. But here in these plots, you can see how human learners generalized in an artificial language learning setting, given some impoverished input. In this corner and this corner, you have sort of the typologically plausible generalizations, and everything else is sort of typologically implausible. And you can see, there's some noise here, but by and large, the participants tended to generalize these artificial languages in ways that are consistent with linguistic typology. Okay. So where do BabyLMs help with this? Well, first, you might ask, okay, do humans really have a learning bias? This study by Culbertson that I just presented is based on an artificial language learning experiment. This is the artificial language that they had people learn. It has 10 words, right? So this makes sense because you're getting people to sit in a laboratory and learn a fake language. You can't have them learn a whole language from scratch like an infant would. But it might give you some cause to question whether the learning biases that we observe in this setting are the same that we observe in first language acquisition. Okay, and then language models can help because we maybe can get a much better sense of whether language models do have this type of learning bias. And if they do, then based on this assumption that the space, samples from the space of possible language learners tend to look similar to each other. If language models do have this learning bias, why would we question that humans do? It would also give us converging evidence that agrees with these experimental results. And then second is we can perform controlled experiments on scale with language models. Right? So I talked about these guys before. What we can do with language models is actually train them at the scale of human language acquisition using a corpus that's equal in size to the input to a child, but actually control the grammatical properties of that corpus. And this is really helpful because it can help us answer this second question, which is, I've sort of talked about the fact that people think that humans have this learning bias, but there's actually disagreement about where this learning bias comes from. Right? Is it a language-specific bias or a domain general bias? So an example of language-specific bias might be something like universal grammar, whereas a domain general bias might be something like a simplicity bias or Occam's razor. Right? This is a bias that's been proposed across a lot of domains of human cognition, and it can help to explain these typological correlations because, say if you have a grammar where you always say heads come first and dependents come last, that's a much shorter description. It's a much simpler description than to list out for each pair of elements which one comes first and which one comes second. Okay. As I said before, language models seem to not have some strongly built-in linguistic priors. So they can help to give us a sense of what domain general priors, whether domain general priors lead to this type of learning bias. Okay, so the approach that we take, this is very similar to what Kyle presented in the first talk today. We use this corpus editing approach, where you take some pre-training data set and modify it in some controlled way. This is also something that's in related work by Collini et al. They take a corpus and modify it in a bunch of ways to try to see whether language models have a harder time learning typologically impossible languages compared to possible languages. The thing that's different about our study and their study is their impossible languages. These languages are really impossible, right? They like shuffle words or reverse strings, whereas the languages that we're looking at are a lot closer to this boundary between possible and impossible. So what do? Well, first we construct a counterfactual corpus. We identify 5 different correlation pairs. These are these different correlations of elements, right? Verb comes before object, adposition comes before noun phrase. We take a bunch of sentences from our training corpus, and we get a dependency parse for all of them. And then we simply identify, for each of these 5 things, we identify the verbs and objects, for instance, in this dependency parse, and we swap their order. And we do the same thing for adpositions and nouns in a separate data set, and for all of these things. So we have 5 separate data sets which look exactly like English, but one of these word order correlations has been changed. And then you might also say, OK, well, English is head initial, so you're just getting a bunch of head final rules. What if language models just don't like head final rules? So what we did was we took Japanese, which is a head final language, and modified it in the same way so that it has some head initial rules. And then we trained, so we swapped corpora for English and Japanese to come up with this set of 5 counterfactual languages that are typologically implausible. And we trained a bunch of GPT-2 and LTG-BERT models on both the counterfactual and the original languages. And we also validated how accurate the swapping algorithm was. This validity score is out of 5. It's like a Likert scale judgment on how often the swaps were correct. You can see they're not perfect, but generally the validity of the swap sentences is relatively high. So first, we just evaluate perplexity on the different languages. And you can see perplexity is pretty similar for the original language compared to all of the counterfactual languages. So even though there's some issues, some mistakes in creating the counterfactual language, it doesn't seem to really lead to a huge increase in perplexity or much lower predictability of the corpus. And most of these differences are not significant between the original and counterfactual languages. OK, but we can zoom in into more on the target phenomenon and say, so for swapping verb and object, you can construct minimal pairs where you have Buddy chased the cat versus Buddy the cat chased. If you're looking at the original language model versus the counterfactual language model, these 2 models would make different predictions for which of these sentences is better. Right? So the baseline model should prefer this sentence, and the counterfactual model with object-verb order should prefer this one. OK, so how do language model preferences for these types of minimal pairs develop over training? Well, what we find is that the baseline models achieve really high accuracy very, very early on, whereas the counterfactual models take a much longer time to learn to prefer sentences that have the right ordering of these elements. And you can see the same pattern across most of the counterfactual languages and models that we look at, both for English and Japanese. And these differences are significant in all settings, right? So the counterfactual accuracy is significantly lower than the baseline in every setting. Yeah.
Could you maybe clarify some intuition what it means again for a language to be typologically implausible?
Yeah, sure. So so all of these things are supposed to be correlated. The order of the verb and the object, the order of the adposition and noun are supposed to be correlated across languages. What we do is we swap the order of the verb and the object alone so that all of these things are correlated in English except for verb and object.
So now you don't have the simplicity bias anymore that everything follows the same pattern, like some follow it, some don't.
Right, you have some exceptions to the rule. So some things have to be memorized. So conclusions, well, typologically implausible languages do empirically seem to be somewhat harder for models to learn. The implications for these 2 questions that I set out are, this is converging evidence with these artificial language learning experiments that it seems like a learning bias for typologically plausible languages seems to exist in language models, so why wouldn't it exist in humans as well? And then it also gives some evidence for the domain generality of this bias, right? Because we see it emerging in models that have a domain general learning bias, but no, we didn't build in this kind of learning bias using like principles and parameters or something into language models. Okay, I have a last section on the poverty of the stimulus, but I'm going to skip this because I think we're out of time. But just to close, okay. To close with the question that I started with, why does it matter that babies and language models are the only known language learners? Well, one thing is this comparison between language models and humans can reveal some shortcomings of language models. And maybe we can use insights from one language learner to improve the other language learner. Also, we can use language models to sort of reverse engineer human language acquisition, which can help us to determine the sufficient conditions for human-like acquisition. We can also use these two learners to better map out the space of competent language learners. This is easier to do with two samples than with one sample. They can also help us to suggest what's idiosyncratic about human language learning, and therefore what's likely to be innate. And then finally, they can help us to determine which biases are innate versus domain general. Oh, and then one more is establishing causal relations between the environment and learning outcomes. Okay, and maybe you have some other things that come to mind. Okay, thanks everyone. Yeah, question.
Yeah, as for the title of your talk, that babies and language models are the only language learners, but you mentioned second language learning. So this is a type of language learning, knowing one language already, so I don't know how it can apply to language models, but it's a very different learning style, right? It's a very different learning method, and it's much more rule-based. So I don't know if we can learn anything from learners other than what you mentioned in a comparison of second and first language.
Yeah, that's a really interesting point. I hadn't thought about second language learners as another sample from the space of language learners. I mean, I could sort of try to go back and restrict what I'm talking about and say, well, I'm only interested in statistical language learners, right? Language learners that just consume a large amount of data and come out with some kind of grammar. Whereas second language learners, most of the time, are not learning by immersion, but learning through this sort of more rule-based approach. I could do that, but I think maybe there's also something interesting to be gained from not doing that.
Very interesting. My question really is around what is the fundamental difference between the conditions under which LLMs learn and babies learn, and LLMs, at least ChatGPT, for example, learns purely from text tokens. And in fact, for many years before 2020, there were philosophical debates about whether it would even be possible for a system to learn language from text alone. And GPT kind of put that debate to rest. But the reason that debate existed was that people took for granted that that's not what babies are doing, and that babies, in fact, already know the concept of mom and food and dog, cat, chair, bed, all these things before they acquire language. And so in some sense, they're learning simultaneously the conceptual structure of the world, plus the word tags that go with those things, plus the grammar. But that seems like quite a head start compared to what LLMs are forced to do, at least before we get into multimodal LLMs that might be changing that. So as I was listening to your talk, for example, I thought the stuff at the end, asking what kind of languages are actually learnable by LLMs, is really interesting, and I could get a take-home message from that, because that result didn't depend on me buying into babies and LLMs learn in the same way. It had more to do with what can be acquired and represented with LLMs.
Yeah, yeah, I
So
completely
anyway,
agree.
You get the idea. My question really is, how do you think about this difference between conditions of baby learning versus LLMs?
Yeah, I completely agree. So, I mean, I had this, I don't know if I can find this image, yeah, here. As the developmental plausibility of your model increases, maybe how convincing the results are also increases, right? So, learning from text alone, that's not very developmentally plausible. So you might have good reason to question generalizability of results from experiments on a text-only model compared to a human. But I think the bigger picture is that there are these ongoing efforts to try to design multimodal models. There's, now we're having this interactive learning component of BabyLM. So there's an engineering component where we have to put in the work to build more developmentally plausible models, and that will give us maybe more generalizable results as time goes on, but it's a big undertaking. On the other hand, there are some questions I think that you can answer really well with a text-only model, right? So I forget who mentioned this, maybe it was Emmanuel yesterday, but if you have a model that's strictly impoverished compared to a human, but it can still learn something really well, I'm happy to say that humans can also learn, if you're asking whether it can learn without innate biases, I'm also happy to say humans maybe could learn that same thing without innate biases, because humans have such a big advantage compared to that impoverished model.
I think we are out of time. Yeah, so why don't we call it here? Let's thank the speaker once more.